Hello, and welcome to our presentation on statistical analysis of facial classification bias in machine learning models. Overall, we found that bias has become a key issue with facial recognition. Our team tested two models, DeepFace and Fairface, which are both open source, against the popular UTK-face dataset to evaluate them for potential biases. The results showed that DeepFace had a significant positive bias towards identifying white male faces correctly, while Fairface fulfilled its intended goal of being fair with significantly less bias and better identification overall, particularly for younger and older faces. We recommend further testing these models in the future. Below, you can see our links. Now, for an introduction to the problem. Misidentification is a major issue with current facial recognition models. According to one study by the National Institutes for Standards of Technology, the misidentification rate is 10 to 100 times higher for African and East Asian faces than white ones. And that's a study done on over 100 machine learning models for facial recognition. Another Georgetown study found disproportionate misidentification of African Americans in American law enforcement databases due to overrepresentation in the mugshot training data that was used. The two main areas that this demonstrates biases can occur in are the algorithm's coding and the training data itself. In order to test the pervasiveness of this issue, we decided to evaluate two different facial recognition models with the same dataset using two different sample tests to check for correlations between them. Here are the four research questions we developed to test these things. 1. Are biases prevalent in facial recognition machine learning models? 2. Can we find biases using proportionality testing and by more traditional measurements as well? 3. How does proportionality testing compare to more traditional measurements? And 4. How did the results change when from an overall perspective versus specific subsets within the data? And now for an explanation on that data.
Moving on to the data section. So the data set that we decided to test on is UTK face dataset. It have over 24,000 face images from the internet. And because they're from the internet, you can see in the example here on your screen that lighting are not perfect. Poses can be different across images, and some pictures can be a bit blurred. We think this is actually perfect because we want to simulate real-world uses. The dataset have three essential features. They are race, gender, and age. They are categorized in this format that you see on your screen right now. We also made an assumption that images in the dataset, UTK face dataset, and images in the training dataset for both models, they are not the same image. Because if they are, the model would always give us a correct prediction, and it would not be much of a test. The facial recognition models that we decided to test on are DeepFace and Fairface. DeepFace is developed by Facebook. It is extremely popular in the industry. Its name has been thrown around quite often. Fairface is developed by UCLA. It is specifically designed to mitigate gender and racial biases. We also make some tweak to the model setting as well. That is because we first went DeepFace to its default setting and it did not perform so well. We want both models to give us their best shot, so we test out different settings for both of them. The one that we end up with, or the one that gave us the best performance, are facial detection on and crop images for both models. And
to restate our motivation, we are testing if bias is prevalent in facial recognition machine learning models. We explored if it's possible to find bias using two-sample proportion hypothesis testing. Our hypothesis test is constructed such that the null hypothesis states the proportion of a certain demographic group in the source data, UTK dataset, is equivalent to the proportion of the same demographic group in the output of one of the models, either DeepFace or Fairface. The alternative hypothesis states that they are not equivalent. In lieu of time, I won't read through the formulas presented, but will state the purpose of this test. The purpose being to infer whether or not the proportions using the same demographic subsets between the source and the model are equivalent. In theory, similar enough proportions could indicate that the data originate from the same population. In our construction, if the test fails to reject the null hypothesis, then the model produces a similar enough proportion compared to the same subset within the source. Therefore, a possible indicator of lack of bias. Inversely, if there is enough evidence to reject the null hypothesis, then this could indicate bias. Comparing across demographics, we can construct hypothesis tests to give statistical evidence to questions such as, are the proportions of females between source and fair face equivalent? Or are the proportion of female given that they were Black between the source and deep face equivalent? Therefore, we are able to test a whole gamut of demographic combinations and dive into where and if biases exist. In fact, using this method, we tested 430 different demographic combinations. We'll also be using the more standard measurements of machine learning testing, being accuracy and F1 score. Both of these measurements are taken by using a combination of true positives, true negatives, false positives, and false negatives, all resulting from a confusion matrix after the models are ran.
And now we present the results from running all these hypothesis tests on the output gathered from the two models. The two models, deep face and fair face, were run on the dataset described previously. In this figure, one can see the results of the predictions done by each model, by each factor that was considered, age, gender, and race. Note that fair face tends to outperform deep face, and that age is difficult in the early and older ages for deep face to predict. For each factor category and model, we calculate the F1 score, accuracy, p-value, and power, as described in section 3. We calculate these metrics and hypothesis tests across all categories of each factor, but also with conditional filtering. For example, if you have the test factor of gender, a gender of female, an age of 0 to 2, and race of all, the hypothesis test can be described as the proportion of female labels given that the source age label is 0 to 2 are equal. Note that this table is filterable by all columns. From the previous table we just showed, we extract and highlight key values, namely where we reject the null hypothesis and where we do not, based on our criteria of significance level of 99.7, a power threshold of 0.8, and an F1 score of 0.9. And we note the disclaimer listed here. We show the test values where there is no conditional subfiltering by another category. Then we also highlight the reverse null hypothesis decisions made for a subcondition and for the specific rows as described here.
In this figure, we show F1 score versus accuracy for all hypothesis tests that were performed. As can be seen, the relationship between the F1 score and accuracy is not perfectly linear. Deep face tends to follow a trend throughout, whereas fair face generally tends above the lines. In these both figures, we explore our research question of whether or not two sample proportion tests can approximately predict the performance of a machine learning model. That is there any correlation between the p-values in the F1 score? In each plot, we transform the p-values to 0 in cases where we would reject the null hypothesis, and 1 in cases for which we would fail to reject. As we can see from the plot above, there is no strong correlation between the two sample proportion tests and the F1 scores. Now we look at the meta-analysis confusion matrix. So these are the rules by which the matrix is built. F1 and accuracy are used to predict the model's performance. We build the confusion matrix to compare our proportionality testing method against the F1 score. When we reject the null, there is a possibility of poor or overperformance, whereas failing to reject showcases the absence of evidence of poor or overperformance. This is the confusion matrix. Along the x-axis are the classifications according to the F1 score, whereas the y-axis is for p-values and power. The diagonal signifies cases where both of these classifications match, but the problem lies where they don't. For example, in the particular cell of column number 2, row number 1 on the left side with the number 157, there is a problem with this, that it is not able to predict the model's performance with the p-values as indicated by the darker green cells.
So jumping over to our conclusions. We have found that across multiple subcategories, we could confidently conclude that there were differing source populations between the data sets, whether it was the predicted population or the actual sample coming from UTK face. Generally speaking, there were greater differences in groups and subgroups for deep face than there were for fair face. However, that being said, and probably important for answering one of our research questions, and looking at the previous slides, there was no strong correlation of any type between our p-value testing and the F1 or accuracy scores. And generally speaking, we find that statistically significant proportionality testing is not a strong indicator of machine learning model performance. However, shifting over to our F1 findings, generally speaking, both models perform poorly with Indian and other subjects. Fairface does very well with the young and old, whereas Deepface completely fails to identify subjects in any young or old category. Deepface has overall poor performance, better on female than male classification, and has pretty low F1 scores in many, many categories. Fairface, however, does quite well with gender classification and does fairly strongly in many different categories. So with the fact that we couldn't necessarily derive anything from our distribution of proportions or p-value testing on the proportion test, we're thinking that for future research, we could potentially look at those distributions and say, where there is great overlap, does that mean something more? Does it mean that there is feature similarity between the source and the predicted data sets? More specifically, the training information that was used to train the machine learning models. And then the converse being true, looking at where there's a greater gap between those distributions, do we have less feature similarity between those data sets? All in all, that has been our research, our conclusions. Thank you for attending this presentation and hope you have a great day.